So far the evaluation metrics that we have used are considered, are considering the documents having a binary relevance. That is, it is the relevant, either a document, any document D is relevant or non-relevant. But it is not actually true. As I was saying, some documents can be more relevant to a query and some other documents can be less relevant to the same query. So we need basically a non-binary relevance. Particularly, we need a graded relevance where we can specify that a document is highly relevant, for example, this, and we can also say a document is fairly relevant, for example, this. So as you can understand, in the web search, we have also, we observe or we realize that the relevance is not actually binary. The relevance is actually graded. I mean, inside our mind, we are actually considering, okay, the first document, which is, let's say, Wikipedia page, is highly relevant. The third document, let's say, in the rank, it is containing some aspects of our queries. So it's not a very highly relevant, but it is, at some aspect, it is relevant, and so on and so forth. So the result that we get after performing a web search is essentially, we, in our mind, we actually consider a graded relevance. So far the retrieval, the evaluation metrics that we have used considers a binary relevance, whether a document is relevant or non-relevant. But as we are observing that graded relevance is actually important, we need to have evaluation metrics which can address this kind of a graded relevance scenario. So in case of a graded relevance scenario, we consider two assumptions. Number one, so highly relevant documents are more useful than marginally relevant documents. So this is more relevant, this is a little bit less, this is some more or less, this is fairly or moderately relevant or less than moderately relevant, you can consider, and this is not actually non-relevant or badly relevant. This is the first assumption. And the second is, lower the rank position of a relevant document, less likely that document will be examined by the user, and less likely that the document will be useful for the user. So if a document, say DI or say DJ, let's say it is relevant, let's say it is highly relevant, but if it is present at, say, 9th location in the rank rather than in the top 5 position, maybe it is less likely to be examined by the user. How much relevant it could be, as the retrieval model is retrieving a highly relevant document at the 9th place, the retrieval model should be, the evaluation of the retrieval model should be done in such a way that the retrieval model should be penalized for retrieving a highly relevant document at a fairly low position. Let's say this is the relevance rate for this is, say, 1 and this is, say, 4. A good retrieval model should retrieve DJ at the first position because it is having the relevance score 4. So lower the rank of the relevant document in the rank list produced by the retrieval model, less likely it is to be examined and less useful it will be to the user. So we should be penalizing the retrieval model for retrieving such a document, such a relevant document at the lower rank. Not actually lower rank, but at the lower ranked position. So considering the graded relevance, there is a very famous evaluation metric that is called normalized discounted cumulative gain. So first of all, what is cumulative gain? So the idea of cumulative gain is highly relevant documents are more valuable, of course, than marginally relevant documents. This is the assumption that we are considering. And documents ranked low are less valuable. So these two are basically the founding stone of this NDCG, in short, or which is called normalized discounted cumulative gain. So there are four aspects in this, basically in this evaluation metric: normalized, discounted. This is the first component. This is the second component. This is the third component, and this is the fourth component. So we start with the gain. Then we will be considering the cumulative gain. Then we will be discounting it, and finally we will be normalizing it. So what is gain? Gain is basically the relevance score or relevance value of the documents. So considering a 4-scale graded relevance, where so this is highly relevant, HR, this is say relevant, this is say low relevant, and this is say non-relevant. So these are the four grades that are, let's say we are considering documents having these four grades. That is, given a query, any document can be either having relevance score 0. In that case, for that query, this document is non-relevant. In case the relevance score is 1, that means it is low. I mean, it is loosely relevant to the query. If the relevance score is 2, it is moderately relevant to the query. And if the score is 3, it indicates that the document D is highly relevant to the query. Now let's say our retrieval model M is producing a ranked list like this. The first document it is retrieving is having, basically is highly relevant, then relevant, then again highly relevant, then a non-relevant, then again a moderately relevant, then relevant, then highly relevant, non-relevant, and so on. So this is actually the ranked list. And as you can understand, this is the thing that is returned to the user. So considering the ranked list, we understand that from our real life Google search or web search, we know that, I mean, in most of the cases, we start examining the document from the very beginning. First, we examine this, then we examine this, then we examine this, and we, like this, we go on deep into the ranked list. So, if we consider the relevance score as the knowledge gain, KG, or let me write it fully. If we consider the gain as the knowledge gain of the user, then after reading the first document, in this case, the user is gaining a knowledge amount of 3. Then after reading this, before reading this, the knowledge gain was 3. Now after reading this, it is basically 3 plus 2, because the grade of the second document is 2. So the total knowledge gain is 5. Then again it is 3. So the total knowledge gain is basically 8, and so on. So after reading, say, n number of documents, the total gain of the total knowledge gain of the user will be basically the summation of I equals to 1 to n, the gain or the score. We can also consider this as a grade with G, or let's consider it as a small g, grade of the ith document. So this is called the cumulative gain. So for any rank I, so CG1 is what? CG1 is basically the gain up to rank I. So in this case, it is basically 3. Now CG2, what is CG2? CG2 is, note that here it is I, here it is J, isn't it? So we are basically iterating the, so I think, sorry, I had made a mistake. It will be basically J. So cumulative gain up to I is basically the summation of the gains for all the documents that we are retrieving from I to, from basically 1 to I, and this is basically the gain. So this will be J. So here it will be basically 3 plus 2, which is 5. Then for, say, let's example say 3G5 as a CG, the cumulative gain 5 up to rank 5 is basically 3 plus 2 plus 3 plus 0 plus 0, which is basically 8, and so on. So we started with the gain. And what, after reading say n number of documents, the user is actually gaining a cumulative gain, or a compact, or a total knowledge gain. You can consider this as the total knowledge gain after reading say n number of documents, which is we are referring to as CG, cumulative gain. Then we'll be discounting it. We'll be discounting the cumulative gain. Here the discount, so the background of this discounting is basically if we are observing a relevant document, a set of relevant documents, although this is containing a relevance score of 3, it might be the case that these two documents are maybe containing similar documents, similar information. So although the cumulative gain, I mean, in cumulative gain, we are adding them up, they should not be actually added in this kind of a simple way, or we should not be computing their simple addition in order to compute their gain, or in order to compute their cumulative gain. So we need to discount it. So again, I'm repeating. So let's consider this document is containing basically this content. So the third document D3 and the first document D1, let's say it is containing the information, and basically there is an overlap between the information. So after reading D1, we have gained this knowledge. So after reading D3, I mean, if we examined, or if the user examined the document D3 in the beginning, he might be gaining the knowledge 3, a total knowledge gain of 3. But after reading D1, it might not be the case that he will be, I mean, considering or he will be reading something entirely new. Some of the overlap can be there. Considering that, will be basically log normalizing based on the position of the rank. Note that here I is the position of the rank, and there is a parameter here. You can see it is log base B. Usually it is considered that the log is considered as 2. So in which case it is basically, I mean, if the rank is less than 2, basically if for the first document, it will be the cumulative gain. So if we again consider this 32300, 3230001. So here cumulative gain is 3, discounted cumulative gain is also 3. If we consider log value or the log base as 2, that is if the rank is less than 2, that is if the rank is 1, this is the rank 1, this is the rank 2, this is the rank 3, this is the 4, 5, 6, isn't it? So here and afterward, so basically what we are doing is we are considering the first document, the discounted cumulative gain of the first document as it is, as the cumulative gain, and for second document onwards we are considering the addition. So basically this is the cumulative gain that we have, or the discounted cumulative gain that we have achieved so far before that rank. So DCG1 will be 3, but DCG2 will be, you can see it is DCG2 minus 1, basically DCG1 which you are saying DCG1 is basically CG1 plus G2, that is the gain 2 is this, divided by log of 2 by 2 or 2 base 2. Okay, so basically you can understand that this is one. This is also another thing. So whenever, as we are assuming, a document ranked lower are less valuable, right? So here with this log factor, we are actually considering that information as well. So for the second document, this dividing factor will be what? Log 2 base 2, which is basically 1. For third document, which is log 3 base 2, which is basically as it is divided by a, it will be basically greater than 1. I think it will be 1.6 something. For 4, it is basically log 4 base 2. So it is basically 2. So you can see the dividing factor is increasing. That means although the gain can be a huge one or a significant one, we are normalizing it, or we are discounting it, not actually normalizing, but we are discounting it by the rank position at which that document is retrieved by the system. Note that all this we are doing in order to evaluate the performance of a system M. This system M, for example, so BM25 has given this rank list for a given query. We want to measure the performance of M for this query in terms of NDCG or some measure. We are not defining, we haven't defined yet what is NDCG. For using some mechanism, we want to basically measure the performance of the system M. Now, as a document which is retrieved at the lower ranked position, they should be penalized or they should be discounted, even though it can be a huge, highly relevant document. So this can be a 4 as well, or in this example, we are only considering gain of 3. So it can be a 3 as well, which is highly relevant. But if the document, if a highly relevant document 3 is basically retrieved at the position, say 16, then instead of considering in the cumulative gain, we are considering the gain as it is. So we are just adding it up. But in case of a discounted cumulative gain, what we are doing is, instead of considering 3, we are considering 3 by log of the position at which it is retrieved with the base of 2. So it is basically, instead of considering a grade of 3, we are actually considering a grade of 3 by 4. So every time we are observing a document at the lower rank, its importance to the user will basically degrading. That's what we are achieving using this log discounting. Is there any question? This is very important. All right. And finally, what we'll be doing is, we'll be also considering an ideal gain. For an ideal gain, the document should be retrieved following their gains, the individual gains in a basically a descending order. So basically, the ideal gain will be achieved by an ideal retrieval system, say MI. An ideal retrieval system is what? Which retrieves the most relevant documents at the beginning, most rel docs at the beginning, at the top position, at the top, then the less relevant documents, then less relevant docs at lower rank, and so on. So basically, an ideal retrieval system will be retrieving the documents based on their relevance score in the descending order. First, all the documents having relevance score 3 will be retrieved. then 2, then 1, then 0. In that case, it will be basically giving the ideal gain. So what we'll be doing is we'll be computing the ideal discounted cumulative gain. And we'll be computing the discounted cumulative gain, and we'll be basically to compute the normalized discounted cumulative gain, basically dividing the discounted cumulative gain at a rank position I by the ideal document discounted cumulative gain at that position. So again, NDCG or normalized discounted cumulative gain is computed at a particular rank position. Let's say it is, so if I consider I equals to 5, then NDCG at 5, NDCG is called at 5, is basically the DCG at fifth location by the ideal DCG. Now, ideal DCG is what? Ideal DCG means if an ideal system retrieves the documents in an ideal way, what will be the absolute ideal gain? So let's say the relevant document, the document scores are basically say 3, 2, 3, 1, or say 0, 1, 3, 1, 1, and so on. So if we consider NDCG at 5, we are basically considering up to this 3. This is the system M. We are evaluating the performance. For the ideal system MI, the document should be retrieved first 3, then again 3. So let's say these are all the documents in the system. Then 2, then 1, then 1, 3, 3 done, 3 done. Oh, there is, sorry, there are 3 3s, then 2, then 1, then 1, then 1, then 0. Up to rank position 5. So this is the ideal. I mean, the ideal system will be retrieving these 5 documents at the top positions. So the ideal gain will be 3. The ideal cumulative gain would be 9, basically 12. But we'll be computing the discounted cumulative gain of this system, discounted cumulative gain of this system. We'll be basically dividing them to get the NDCG or normalized discounted cumulative gain. So let's consider an example. Let's say the documents are say D1, D2, D3, D4, sorry, and D5, having retrieval relevance scores at 2, 1, 0, 3, 0. This is retrieved by a system M. We need to compute the NDCG at 5 for this system. We need to compute this. So first thing is we need to compute the cumulative gain. So you can understand the cumulative gain is basically 6 CG why have I written this as 3? Question mark. Yeah, so first of all, we will be computing the CG at 5, which is 3. This is not actually needed here. This is not actually needed. Still. So now if we compute the DCG at 5, what is this? The DCG at 5 is basically the CG at 1 plus, for the second rank, it is basically DCG So let's go step by step. It will be easier for you to understand. DCG at 4 plus G at 5. So G at 5 is basically 0 by log 5. So this is 0. So DCG at 4 means DCG at 3 plus this positions CG, basically CG by log of 4 plus again this 0 for this. DCG at 3 means DCG at 2 plus DCG at, I mean, for this location, which is again 0 by log 3 plus 3 by log 4 plus 0. Now DCG at 2 means this at this location. So it is basically CG at 1 plus, so as we have defined this, so we are at location 2 here. So 2 is greater or equals to the base we are considering. Here we are considering base 2. So what we'll be doing is we'll be basically, okay, let's write in that way. It will be easier for you again to understand. So still we'll be computing DCG at 1 plus, so for this location it is the relevance or the gain is 1 by log of basically log of 2, basically the second location base 2 plus this 0 for this plus 3 by 4 or log 4, sorry, plus 0 for this. Now DCG at 1, when 1 it is 1, it is basically less than b. Here b, the value of b is 2. So here we are computing DCG at 1. So it will be CG at 1. CG at 1 plus this is 1 by basically 1 by 1 log 2 plus 0 plus 3 by, basically I'm directly writing it 2, basically log 4 base 2, and finally CG1 is basically 2, isn't it? So the cumulative the DCG at 5 is 2 plus 1 plus 0 plus 3 by 2 plus 0. So it is basically 3, basically I think 4.5. Okay. Now this is the DCG. Now we need to compute the ideal DCG. So for the ideal DCG, we'll be computing the basically the entire thing. So basically, yeah. So for the ideal scenario, so let me write it quickly. So this is the DCG. So now ideal DCG at 5 is when it is ranked following this manner. First 3, when D4 is retrieved, then D1 is retrieved, that is 3, 2, then D2 is retrieved, then D3, and D5, 0, 0. So DCG at ideal DCG at 5 is basically, if we do the computation, it will be basically 3 by log 2 plus 2 by log 3 plus 1 by log 4. Oh, no, sorry. So it will be basically, sorry, I missed this part. It will be 3 plus 2 by log 2, because it's ranked in the second position, plus 1 by log 3 plus 0 plus 0. So it will be something like 3 plus this will be 4. So 4 plus 1 by log 3. So the NDCG.
Excuse me, sir.
Yes, you have some question. Yes, yes, please go ahead.
Sir, what is the cumulative gain at 2? Is it 3 or is
This
it
is not this.
1?
No, so the for M, so
Normally, like,
this is MI. So for normally, what you were saying, can you please repeat once again?
so the cumulative gain at any point is the sum of all the ranks at
Cumulative,
that point and above, right?
exactly, exactly. No, sorry, it should be 6. Extremely sorry. 2 plus 1 plus 3.
And
So cumulative gain at 1 is 2, cumulative gain at 2 is 3, cumulative gain at 3 is 3, cumulative gain at 4 is 6, cumulative gain at 5 is also 6. So it's
yeah,
not
okay,
actually
so
needed.
that way these calculations will also be.
Yeah, but does it make sense, or do you have any question? Do you have any doubt?
Yes, yeah, now it's fine. So now
No, no,
the
I have
other
written it
calculation
wrongly
that
as
you have
3.
done.
No,
Yeah,
earlier I
okay.
was written this CG at 5 wrongly as 3. It's by mistake. So now this is the ideal DCG, and this is the basically the systems DCG. So it will be basically,
Yeah, no, so this CG that you are using for, okay, so should we use
yes, tell
CG
me.
or can you show the formula once again?
Yes.
Okay, okay, yes, yeah, okay, now it's clarified. Thank you, sir.
So yeah, so here we are basically, so this will be the NDCG at rank 5. So this divided by this. Okay. So any question up to this? Oh, I have made a mistake here. I think this will be 5, because 3 plus this is 2 by 1. Yeah, that's why I'm getting some weird value here. It will be basically 5 plus 1 by log 3. So of course, always NDCG at the top. So NDCG can be having the highest value as 1 when the system is actually performing ideally. When the numerator and denominator will be giving the same value. In all the practical cases, it should be less than 1. That is, it will be performing less efficiently as compared to the ideal system.